IPCC power plants with carbon capture and storage by Dr. Dolan Dobro, Deputy Head Gasification Department and Head of the Process Simulation Group of Gas Technologies, Dyson Group, Uday, Germany. Please, thank you.
Today I'm going to present another presentation from ELCOGAS from Mr. Francisco Peña. And actually my own presentation is today. I thank you, Dr. Singh, for a very nice overview. And she helped me a lot so I can skip a lot of slides from my presentation. For example, the CCS overview, I will skip it simply because it's the same. So we can save some time. Here, I wanted to mention, to give some comments on these three technological options for CCS. So, post-combustion capture and storage, you have a conventional combustion. You can apply it immediately to any boiler, to any power plant. But you have here in flue gas nitrogen, which is atmospheric nitrogen. It is about 70% in your flue gas. So in order to capture the CO2, you need huge mass heat exchangers. And this will cost you about 8 to 10 or 12% more in your efficiency. So if you have a power plant operating with, let's say, 35% net efficiency, applying CCS here, you will have something like 23-25% efficiency. Similar situation is in oxygen combustion. This is one very intelligent way to avoid the atmospheric nitrogen in your flue gas. But you have to produce oxygen. And production of oxygen is a major technology. It's well known, but it's very power intensive. And the production of oxygen will reduce your net efficiency with about, again, 8 to 10%. If you have to compress the CO2, then you get another 2 points less. So, in these cases, for us engineers, there are a lot of challenges to find out how to make this process more efficient. But for politicians, there are also a lot of challenges to create a framework so the private sector can collaborate with CCS. And today I will talk about the pre-combustion and the experience from ELCOGAS on CCS. Okay, this I will skip, it was already mentioned. So, pre-combustion due to capture and gasification. This is a simple gasification process where you supply oxygen and wood, you gasify the wood, you produce a syngas containing mainly carbon monoxide and hydrogen. Then you apply a shift reactor to convert the carbon monoxide to carbon dioxide and to produce hydrogen. And then you have to split the hydrogen from the carbon dioxide. Carbon dioxide should be pure, and then it can be compressed, liquidated, transported, and stored, or used for other purposes. And the hydrogen you can cook up, or you can sell simply as a chemical in the free market, or you can burn with air in a gas turbine, producing electricity. The flue gas, the sensible energy of the flue gas can be recovered in a heat recovery steam generator, which can drive a steam turbine and produce also electricity. Just in combined cycle, you can get better efficiency. Okay, I expect this. The existing technologies, syngas production can be made via natural gas reforming, oxidation, autothermal reform of methane, or gasification of solid food. The CO2 CO2 conversion can happen via water-gas shift reaction. Separation of CO2 from H2 can happen using chemical or physical absorption of the organic membrane. And the purification of the hydrogen can lead to absorption, radiation in membranes, or cryogenic distillation. The emerging technologies are a combination of existing technologies. Water-gas shift membrane reactor, reaction plus membrane, or solvent enhanced water-gas shift, reaction plus absorption. This I will skip because mentioned the increase of gasification plants worldwide, where they are distributed. Existing gasification plants worldwide are IGCC plants. There are 2 nowadays operating in Europe, Elbogas and Prešova in Czech Republic, 3 in the United States, 1 under construction, this is in power, 1 in China in operation, 1 in construction, 1 in Japan in operation, and 1 in Korea in construction. Elbogas experience in CCS. As I mentioned yesterday, Elbogas is a private company established in 1992 to undertake the planning, construction, management, and operation of 335 megawatt electrical electricity plant located in Birmingham, Spain. Birmingham is a small city, close to Madrid. Elbogas power plant located here, and it is powered by coal, which was mined in a local mine, and petrol from the local oil refinery. So we have power block, gasification plant, and air separation unit. Once again, the coal and the petrol are mixed with 50-50, 50% coal, 50% petrol. There's also some limestone in addition in order to control the ash melting point, because the gasifier is a Franco type, so it is Franco gasifier slagging, operating at temperature above the melting point of the ash. The gasifier has a high pressure boiler and middle pressure boiler, where the gas is cooled, produced gas is cooled down, then it is adjusted in a normal ceramic filter. And then in the stopper, the chloride is removed, and small particles also. Then we have sulfur removal using ammonia, and in a normal glass facility, the sulfur is recovered, and the cleansing gas is burned in a gas turbine, producing 200 megawatt electrical power. The flue gas are transported to the heat recovery steam generator, where using also high pressure steam and middle pressure steam from the gasifier, and they are driving this steam, driving the steam turbine, producing another 135 megawatt electric. The gas turbine is driving the air separation unit, producing oxygen, which is required for the gasifier. In this case, the oxygen is not very high purity, it's 85% oxygen. And the remaining nitrogen from the air is used for cold drying and cold transportation. Elbogas has established its own research and development program with 6 main topics. Yesterday I explained about more details about this main topic. And one of the topics was DEC CO2 project, the framework of this project, to build a pilot plant for CO2 capture and hydrogen production. The main aim is to demonstrate the feasibility of the CO2 capture and hydrogen production in an IGCC that uses solid fuels and fossil fuels and wastes as main feedstock. Elbogas has IGCC, So they can use real gas, real conditions, and to test this technology. There are several participants in this project, and the project was funded by the Spanish government and by European Union. The power plant was built and it's in operation since October 2010. The first worldwide installation of this type is about 40 megawatts of size. The construction costs are about 13.5 million euro, 1,100 working hours operated until September 2013. 3,500 tons of CO2 were captured and 6 tons of pure hydrogen were produced. It is intermittent operation, not continuous operation, just because this pilot plant was made for test. This is how it looks. The control room is here, the CO2 absorber, the CO2 stripper, the water dashing reactors, and the pH absorbers. I will show you now in more detail how it works. So, it was taken from the main gas, from the main stream, about 2% of the gas. Two types of shift were tested, sweep and sour. This means sweep shift. If we apply sweep shift, we take the gas after the sulfurization, so there is no sulfur in the gas. Go into the reactor. For the sweep shift, we have catalyst based on iron chromium. And the second shift is sour, which was tested. So in this case, our catalyst can live with sulfur, let's say. So you can skip the sulfurization unit, and you can take some gas samples from the after the filtration, and then the catalyst which were used was based on copper. So you see some figures for the two options. After the gas was shifted, then the CO2 and hydrogen were separated in a separation unit, and the hydrogen, raw hydrogen, which still has 80% purity, is additionally purified in PSI unit. And then high quality of hydrogen was produced. And then all these gases were accumulated in a buffer and transported back to the main stream and burned in the gas provider. So the idea was here not to produce hydrogen instead, whatever, just to test all this stuff, all this technology. So let's have a look more details on the different units. The conversion unit. In this case, gas, syngas, is coming into the column, it's the shift column, where it is mixed with steam, and the CO2 shift reaction takes place. This is an exothermic reaction, so you have some energy losses, and in this case, the gas is heated up to about 180 degrees, and then you cool down the gas, producing some steam. Then it comes to the next reactor, the second reactor, for further shifting of CO. And after that, if you cool down the gas and then produce some electricity, air cooler, and then you leave the system. So here you can see the composition of the gas as it comes from the gasifier. So you have about 60% CO, 22% hydrogen, and about 2.0% CO2. Then here, this is the composition of the gas after the first stage of the CO conversion. between the two reactors, let's say between the first and the second reactor. So you have already 10% CO from 60 to 10%. And this is the composition of the gas after the second reactor. So you could reduce the CO composition to 2%. Further reduction is almost impossible. So the next step is the separation unit. So the shifted gas consists of an absorber where activated MDR is coming inside, absorbs the carbon dioxide. Then this carbon dioxide with the MDR is going to a stripper for regeneration. The carbon dioxide is separated, pure carbon dioxide, and the MDR is recycled back to the absorber. The CO2-free gas is leaving the system. In case of the sweet shift, we have reduced we can capture about 99.8% CO2, so very high content of CO2 in the gas, and in case of SOR, 98.2%. Here are some numbers about the separation unit. So the design numbers and the real-based numbers. This is very valuable information because this data is based on real gas, gas. The next step is PSI unit, where the hydrogen should be purified. So they're all hydrogen-containing gas. That's for the separation unit, and then it's distributed for absorbers. These are absorbers where just pure hydrogen is extracted in these absorbers, and so we get a pure hydrogen stream, and the time gas, which so the non-converted gas, is collected in this time gas filters. So you can see here for the sweet shift, we get the raw gas about 80% hydrogen, and after the PSI unit, we have 99.99% pure hydrogen. And this is the composition of the time gas. So, main results and learnings. Operation with SOR catalyst was found to be more stable than with the sweet one. This, I think, is a very important result. Second, the conversion stage. 95% of total CO conversion takes place in the first reactor. Do we need the second one? So this is a measure play off in the course and the conditions which we require for the purity of the gas. So in the first reactor, we get about 10.6% CO in the gas. After the second reactor, we go down to 3%. The answer, do we need second reactor or just one reactor, is maybe in the application of the syngas. What do we want to do with the syngas? Do we want to burn it? Do we want to sell it as a hydrogen, or to do something, other things like synthetic fuels, etc.? So these requirements will define how many reactors do we need. The steam consumption in CO shift. This is a key parameter for efficiency in capture ratio. The test showed that an increase of 30% in water gas shift steam consumption counts as an increase in 1% only in CO conversion. So in these cases, it's also a trade-off. Do we need, as I am presenting in the UDE, we have bread flow with steam generation or bread flow with direct wedge, which means we saturate our gas already in the gasifier. In this case, we can save a lot of steam is a trade-off. What for we need our syngas, what the application are the time. There are some regulations done concerning the CO2 capture cost. So, in case of sweet ship, where you have desulfurization unit and CO2 capture afterwards, we can establish the cost, we can calculate the cost of CO2 not emitted. It's a ratio between cost of additional carbon capture unit and the amount of CO2 not emitted. The capex scaled up for the IGC plant in Guatemala will be in the range of 350 million euros to capture about 90% of the CO2. The OPEX were calculated in the range of 400,000 euros per year. You should consider that applying CO2 capture will reduce your efficiency. For the case of Puerto Llano IGCC, the efficiency at the moment is 42% net efficiency. And if you apply 90% capture of CO2, you'll get efficiency about 23% net efficiency. You have to pay for it. And in this case, the cost of CO2 capture will be about 26 euro per ton captured carbon dioxide. You have to capture it, but then if you want to store it, you have to compress it. So, including the compression to 150 bar, it will cost you 35 euros per ton capture and compressed carbon dioxide. There was some sensitivity analysis that is done for different operating hours of the power plant in the year and the net efficiency with the CO2 capture loss. So you can see simply that if you operate at maximum rates, about 7,500 hours per year, you will get, you will be the most efficient way. This means that if you have to apply CCS, IGCC, your IGCC has to run on a base mode. So it has to provide the base electricity, not to cover just the peaks. Otherwise, it will be not profitable at all. So, a plant which integrates a carbon capture unit should operate on a base load mode. And even if the plant in base load, a poor availability of the capture unit can nullify any improvements achieved. So, the effect is denoted on efficiency and availability. So, sort of swing operation mode. As I mentioned yesterday, Ecogas concluded that the CO2 capture post retrofit is estimated at 350 million euro, approximately represents the cost of the desulfurization and sulfur recovery units in an IBC without CO2 capture. So, by studying an IBC with soil capture, to store or use CO2 together with 1.5% H2S, the investment cost in this case will be similar to those without capture, because in this case you omit the desulfurization and sulfur recovery. But you have to consider the energy penalty, which for the IGCC plant in Guatemala, as I mentioned already, will be from 42 to 33% reduced. And for new IGCCs, which now can be designed with the newest technologies available, with a net efficiency about 50%, the reduction will be to estimated to 44% net efficiency. So, having the CCS in IGCC, you have also the possibility, so you are producing hydrogen. So you have the possibility to burn the hydrogen, to produce electricity, go for hydrogen or to sell the hydrogen. And the cost of hydrogen in Ecogas will be about 1.3 euro per kilogram, and current price of hydrogen in Spain is between 8 and 15 euro per kilogram. So it is much more profitable to have to sell hydrogen than to produce electricity. Okay, just concluding very fast. Ecogas Berkeley plant is available. In Ecogas is available a singular and unique industrial facility which captures CO2 and produces high-purity hydrogen integrated in an operating plant. Ecogas power plant project has been a success. First of its type in the world, carbon capture ratio higher than 90% and capture cost can be under 30 euro per ton without optimization. Pilot plant is being used for internal research and is also available for international research projects and for other kinds of cooperation if there is interest from other partners. Thank you for your attention.